Hello, crazy math nerd. It's the craziest math nerd of all, Kitty Morgan here. Want to have a discussion about how continuity and differentiability work together or not. There you go. So what does it mean to be differentiable? This particular unit is full of vocabulary and so many words mean the same thing. And differentiability, or something being differentiable, means that every point has a derivative, which means every point you can draw a tangent line to. And just like in continuity, when we didn't really look at every point that was nice and smooth, we looked for bad points like vertical asymptotes or jumps or breaks or things like that. We're going to use that same process to talk about differentiability, because on nice smooth functions, graphs can have a tangent line drawn and we can find that slope. But there are some places that are tricky where we cannot find a derivative. Okay, so that's what we're going to talk about today. So first of all, notice I have put the definition of the derivative up in red, and that definition says that you want to find that slope between 2 points, and as the points get closer, that slope becomes the slope of the tangent line. So really what that definition, it's the limit of the slope of the secant line. That's really what the, I'm going to get a different color real fast. There we go. Okay, that's really what that is. So the derivative is really a limiting of the slopes of the secant lines. Well, a limit can only exist if the limit from the left is equal to the limit from the right. And what does that mean? Well, if I were to want to know about the limit of 0 for this graph, that little point right there, then as I drew secant lines and brought it in, notice that both sides are approaching a slope of 0 for those secant lines. So the limit as you come in, I'm so sorry that moved. So the limit as you come in, limit as h approaches 0 from the slope of the secant line for the left would be the same as the limit. So what you're trying to do is you're trying to see if the slope of the secant lines are the same, coming in from both directions. And let's see if that's true for a corner. Well, to show you this, I'd like to use another program. So I'm going to close out of this and open this up. And this is actually a Geometry Sketchpad applet. So notice that here I have a line that's to the left of 0, because that's my questionable point. See, this from here to this corner right here, for all of that doesn't bother me. That is smooth and continuous. And it's smooth and continuous on that side as well. So what I'd like to see is it smooth and continuous at 0? Well, let's look. That slope will be -1 all the way down. So the slope from the left, oh, and look what happens when we get it at 0. It becomes +1. Here it comes back down. Come on, buddy. It's coming back from there we go. So coming in from the right, the slope is +1, and from the left, it's -1. So because those slopes do not match, we say that the point, not any point, but just the point where that corner is, so at 0, and make that sharper. That's terrible, y'all. So sorry. I'm trying to draw on the surface. I'm not doing very well. Then the slope at 0 is very sharp. And so coming in from the left, the limit, and right over here, the limit in this case is -1, and coming in from the right, the slope is +1. So because the slopes are not coming in to approach the same slope, then the limit does not exist. And if the limit does not exist, then f of x is not differentiable there. Okay? So at a corner, the function at that point is called non-differentiable. Non-differentiable. So it is non-differentiable. Differentiable. But only at that point where the corner is. All the other points are fine because it's smooth everywhere else. Okay? Now, let's look at what a cusp is. A cusp is like the x to the 2/3 graph. So again, I'm going to go make this small and find a helping hand here. And made it go small. So let's go do this. I think that's my cusp. And there he is, Mr. X to the 2/3. Now watch what happens as the secant line approaches. See, the secant line A and B have 2 points. And what happens as it's going away. So in just a moment, we will find out what happens when the secant line actually comes. All right, here we go. So here's the secant line between A and B. And as A gets closer to B, what kind of line do we have? What kind of line? Look real fast. It's going to happen fast. Happen fast. There it is. Oh! What kind of line was that? It's a vertical line. Okay? It is a vertical line. And if we wait for it to come back, coming from the other side would also be a vertical line. So this particular example is not, there we go. This particular example is not differentiable, not because the limits aren't the same. It's because the tangent line that it makes is actually a vertical line. Lord, it's actually a vertical line, and a vertical line has undefined slope. And so that limit would be undefined. And so because of that, we say that there's a non-differentiable point only right there because everything else is nice and smooth. But at that that's kind of a corner cuspy kind of thing, just like the absolute value is. So at that cusp, and that's called a cusp, that x to the 2/3 right there, then we say that that is a non-differentiable point at the cusp. All right, there's one more guy to look at that's a graph, and then that is x to the 1/3, or what I call a go vertical. It's where your graph kind of is going along, and then all of a sudden it goes vertical. So let's take a look at that. And let me go back and pull that up for you. And here we go. Hopefully that's it. There we go. And let's animate the point. Now notice, see, as A goes to B, what kind of line do we have again? We have that vertical line. And so because as A approaches, when A goes to B, the line goes vertical. That means the slope is undefined. And so again, we have that non-differentiable point. Okay, so there are different reasons why points are non-differentiable. 2 and 3, the cusp and go vertical, the x to the 2/3 and x to the 1/3, is actually for the same reason, because their tangent line is actually a vertical line, and the slope of a vertical line is undefined. So be very careful, and that's only because when I pulled the secant in, it went to that vertical. You have to be very careful. That is why. So if you have a corner, a cusp, or go vertical, then at that cusp, corner, or go vertical, you have a non-differentiable point. Now the last one's just kind of common sense. If the not continuous point, if you don't have a continuous point, you cannot draw a tangent line to it. Therefore, it cannot have a slope. So if you have a point of discontinuity, then you're definitely going to have a point of non-differentiability. So that brings us to the next point. What is the relationship between continuity and differentiability? If a function is continuous, it's not necessarily differentiable. Not necessarily. It probably is, but we've got those 3 places to look for, right? And if a function is differentiable, is it necessarily continuous? Yes. Because we know that if something is differentiable, it had to at least be continuous, and it had to have a point defined. It had to have that tangent line drawn. So if a function is differentiable, you are implying that it is continuous. So here is a statement that you can use. If a function is differentiable, then you know it has to be continuous. That's something you're going to use a lot. That's like a definition that you justify your answer with. If a function is continuous, it's not necessarily differentiable. We've got the three places we're going to look for. And if a function is not continuous, it cannot be differentiable. I mean, you just can't do that. So if it's discontinuous, then it's also going to be non-differentiable there. All right. So I hope that helps you understand a little bit about the relationship between continuity and differentiability and the different reasons why number 1 is non-differentiable is different than 2 and 3. So I hope that helps a little bit. Now go work on the Benita Albert worksheet on the back of 3.1, 3.3 and see if you can find all your points of non-differentiability. Thanks, hope this helped, and come back again.